When a high volume of complex carbohydrates, like a pristine plate of white rice, enters the digestive tract, it initiates a severe physiological stress test known as a postprandial glycemic excursion. For an individual with an insulin-resistant profile, rapidly ingesting this starch load overwhelms the system. The body struggles to clear the sudden influx of glucose, resulting in a damaging and prolonged blood sugar spike. To manage this, clinical research points to an exogenous intervention, acetic acid. This is the primary active compound found in highly dilute solutions like apple cider vinegar. Popular internet trends frequently mischaracterize this liquid as a direct thermogenic agent that simply melts away body fat. That is biochemically false. Instead, acetic acid operates as a highly specific biological agent. When ingested, it actively alters the pharmacokinetics of how your body processes and absorbs carbohydrates. It functions as a targeted metabolic brake, applying severe friction to multiple stages of the human digestive tract. For anyone managing metabolic syndrome, slowing down the rate of glucose absorption is a biological imperative, proving to be just as critical as managing the absolute volume of the carbohydrates consumed. To observe the efficacy of this brake, we can track identical carbohydrate payloads processed under two completely distinct biochemical environments. In our control condition, the digestive system processes an isolated payload of complex carbohydrates, a standard serving of white rice. In the intervention condition, we introduce the exact same carbohydrate payload, but precede it precisely 15 minutes prior with a dilute ingestion of acetic acid. We measure the divergence of these models using this Cartesian plane, tracking blood glucose on the y-axis against elapsed time on the x-axis. The total macronutrient volume is identical. The hormonal disparity relies entirely on fractional changes in time. The divergence begins the moment the payload makes physical contact with the enzymes in the upper digestive tract. Complex starches, like those in rice, are structurally organized as tight branching chains of glucose molecules. In this linked state, the human intestine cannot absorb them. To access that energy, the body deploys an enzyme called alpha-amylase. Its sole physiological function is to rapidly cleave these long starch chains into simple, highly absorbable individual sugars. In our uninhibited control model on the left, alpha-amylase slices through the complex starch chains with aggressive efficiency, immediately flooding the local environment with free glucose. In the intervention model on the right, the environment is saturated with acetic acid. These molecules physically dock onto the amylase enzymes, temporarily inhibiting their ability to bind with and sever the starch. Notice the resulting data on our plot. The uninhibited control model rapidly generates simple sugars, creating a steep, acute upward trajectory. The inhibited intervention model forces a much slower cleavage rate, yielding a shallow, highly manageable slope. This severe deceleration of carbohydrate breakdown happens immediately upon contact, entirely prior to the food entering the stomach or the bloodstream. By artificially stalling the upper gastrointestinal enzymes, acetic acid executes a first critical phase required to flatten the body's total absorption curve. Following the initial enzymatic engagement, the physiological focus shifts downward, past the esophagus, to the muscular activity of the stomach and the pyloric sphincter. This lower valve regulates a mechanical process known as gastric emptying, the highly controlled release of digested chyme from the stomach basin into the small intestine, where absorption into the blood actually occurs. Under standard control conditions, a high carbohydrate meal triggers rapid gastric emptying. The stomach quickly dumps its contents, abruptly flooding the duodenum with high concentrations of simple sugars. When acetic acid is introduced into this environment, it acts as a distinct chemical messenger. It signals the localized nervous system to actively delay gastric motility. The mechanical transit time physically diverges. The control model rushes the payload through the sphincter, while the acetic acid model artificially slows the stomach's contractions, holding the contents back. This mechanical transit delay is directly linked to the operational capacity of your pancreatic beta cells, which secrete insulin to clear glucose from the blood. By delaying gastric emptying, the intervention restricts the glucose influx to a slow trickle. This affords a compromised, insulin-resistant pancreas the necessary time to secrete adequate insulin and clear the sugars without being acutely overwhelmed. Beyond localized mechanical effects in the gut, the intervention ultimately exerts a profound systemic effect within the peripheral circulatory system. A portion of the ingested acetic acid is absorbed across the intestinal wall directly into the bloodstream, circulating throughout the body's vascular network. Here, the acid molecules target and interact specifically with peripheral skeletal muscle tissue, connecting directly with individual myocytes. At the cellular level, insulin resistance is defined by the failure of this specific muscle tissue to open its receptors and uptake circulating glucose from the blood. Systemic acetic acid functions as a potent cellular sensitizer. As it binds to the outer membrane of the myocyte, it signals GLUT4 transporter proteins to rise to the cellular surface and actively pull circulating glucose inside. Once pulled across the membrane, those loose glucose molecules are rapidly bound together and stored securely inside the muscle tissue as dense glycogen, physically clearing the surrounding bloodstream. We can quantify this cellular response. This chart, illustrating data published in the journal Diabetes Care, demonstrates that consuming vinegar before a high-carb meal improves post-meal insulin sensitivity by a striking 34%. Applying that 34% improvement metric to the ongoing blood glucose model completes the technical profile of how this intervention manages the postprandial state. Because the skeletal muscle is actively upregulated to clear glucose faster, it physically pulls down the tail end of the postprandial curve, preventing the blood sugar levels from remaining elevated over an extended period. The clinical efficacy of acetic acid relies entirely on this dual action capability. It initiates its work locally as a digestive brake in the gut and culminates systemically as a cellular sensitizer in the peripheral muscle. The completed Cartesian graph tells a definitive story. The control curve exhibits an aggressive spike and crash, while the intervention curve resolves as a flattened arc. The biological paradox is that the absolute volume of glucose absorbed under both curves is mathematically equal. The stark variance in the hormonal response, and the subsequent stress on the pancreas, is dictated strictly by the altered rate of systemic delivery. This proves the overarching clinical principle of nutritional sequencing. How you organize the ingestion of specific compounds dictates the metabolic outcome of the meal. To harness this mechanism, clinical trials demand a strict sequencing parameter. The dilute acid must be ingested exactly 15 minutes prior to the carbohydrate load. The timing is a rigid physiological necessity. The acid requires that 15-minute lead time to travel down the esophagus and coat the upper GI tract, establishing a complete chemical blockade before the physical arrival of the dense starch. Without adhering to this exact and precise sequential timing, the acid arrives too late to inhibit amylase enzymes, and the biochemical benefits of the intervention are completely nullified. Utilizing a weak organic acid as a biological tool demands strict adherence to practical safety constraints to avoid collateral tissue damage. In its concentrated form, acetic acid is highly corrosive. Direct ingestion of undiluted vinegar causes irreversible degradation to dental enamel and soft tissue. The standard protocol requires diluting a single tablespoon dose into a large 8 to 10 ounce volume of water, neutralizing the corrosive threat while maintaining functional dosage. That single dose acts sequentially to blunt the enzymatic cleavage, delay gastric motility, and sensitize peripheral muscle tissue to clear glucose from the blood.
Thanks for watching Body Science School. Please like, share, and subscribe the channel for more.